Welcome students. In this video lecture, we will be covering case 2, that is square slab fixed on all four edges. So it's a square slab with length L and it is fixed on all the four edges. Now when I say fixed, there will be two types of yield lines or yield patterns that will be formed. One is a positive yield line that is shown as a diagonals, and second one is the negative yield line that is developed at the corner due to the negative moment. Okay. So this is shown with dash line, and this is a crooked line which shows a positive yield line. So a square slab is isotropically reinforced. What do you mean by isotropically reinforced? Is the reinforcement in both the direction, that is in x direction and in y direction, is same. So ASTX in x direction is equal to ASTY, that is in y direction. This means that the movement in x direction and movement in y direction were same. That is the reason we provided the same amount of steel. Okay. Now as there are as the edges are fixed, what has happened? I will just note it down here. We have negative yield lines and we also have positive yield lines. Sorry. So this entire slab or the analysis of this slab gets divided into two halves. One, everything due to negative yield line, and one, everything due to positive yield line. We have already seen positive yield line analysis, that is the case 1. So in addition to case 1, we will have to consider the analysis of negative yield lines here. Analysis of positive yield lines will remain the same as we have done in case 1. So a figure shows a slab of span L and length of each negative yield line, that is this length of each negative yield line also will be equal to L, because it is for the entire side. Okay, so length of each negative yield line will also be equal to L. Now if again same condition, if delta is a small virtual displacement at the middle, the rotation of these negative yield lines will be, so we will have to consider what is the rotation of these negative yield lines. So first, to start, this is everything about negative yield lines. This is the first part. Okay, so this is the first part which we have started. So in that we have considered length of each negative yield line, which is equal to L. There is a virtual displacement delta at the center, and now due to this there is rotation that is going to happen in x direction and in y direction. Again, as it is isotropically reinforced, we consider that rotation in x direction and in y direction both are same. Again, that is equal to theta. What it is? Opposite upon adjacent. It is the same way how we have taken for case 1. Okay, so now in this case it is not the diagonal, but it is this particular straight line, this dotted line that you see. Okay, so here if you consider this as the length and this as this will be rotation. Okay, so this will be rotation. If it shifts from here, this is theta, so it will be opposite upon adjacent. Opposite is equal to again delta. Okay, so if I want to draw this diagram, it will look something like this. So this is the negative yield line, which is a dash line. Okay, at the center there is delta. So this is theta, wherein this is equal to L. So half of this, it will be L by 2. Okay, it is about the straight line. It's the same diagram what we have drawn for diagonal here. It is the same diagram for the horizontal line. So this is theta x, also same it will be in theta y, that is for this particular triangle. So if there is a displacement delta at the center, then this theta x upon theta y will be equal to opposite upon adjacent. So it will be delta upon L by 2. Okay, so which this can be written as 2 times delta by L. So here we know the rotation, we know the length, and also we know the moment. We will be able to write the equation for internal work done by negative yield lines. So here internal work done by negative yield lines will be equal to summation of mun into theta n into ln. This is a standard equation again which we are going to use to write the internal work done. Now when I say summation, I need to consider all the negative yield lines. We have 4 negative yield lines here in entire perimeter of the square slab. So it is 1, 2, 3 on top and 4 here. So when I say summation, I need to multiply this by 4 because there are 4 yield lines. Okay, so this 4, this mu n will remain mu, that is the ultimate moment. Theta n, we have got the value as 2 delta upon L, so we will substitute this, and Ln again is nothing but L. Okay, so this is the equation for internal work done, wherein we have 4 yield lines, negative yield lines, so we have multiplied by 4. Mu is the moment. This is the value of theta that we have derived here, and length is equal to the length of the side, which is equal to L. So we can write this as equal to 8 times mu into delta, as this L and L will get cancelled off. Okay, so internal work done due to negative yield lines. So this is one equation. Now so we will see what is the internal work done by positive yield lines. We will only see internal work done first. So positive yield line. Again the equation remains same, summation mu n into theta n into L n. Okay. Now how many negative yield lines do we have? 2. Negative yield lines are the diagonals. So we have 2 diagonals here. We have 2 diagonals here. So negative yield lines number is 2. So we will write it as 2 into mu will remain the same. Okay. What will be theta n? Theta n, again it is same as case 1 that we had considered from this particular diagram. This theta n will be opposite upon adjacent. Opposite is delta, adjacent is root 2L by 2. That is half of this. Root 2L is the length of total diagonal. Half of it, that is this part, will be root 2L divided by 2. So if you just consider as case 1, your theta n, first we have to write it as 2 theta n. Okay, because the total rotation in this case is 2 times theta n into ln. This mu will remain the same, and we have 2 diagonals, so we multiplied by 2. So it is 2 multiplied by mu into 2. Value of theta n is nothing but delta, that is opposite, upon adjacent is root 2L, that is the length of the diagonal, divided by 2 because it is half, and ln is, that is the length of diagonal, is root 2 times L. Okay, we have only substituted the value of 2 theta n and ln. Why 2 theta n? It is the total rotation. This we have covered in case 1, so you can always go back and check. Okay, so here if you do this, then it becomes 2 into mu into 4 times delta upon root 2L into root 2L. This and this gets cancelled, and the final equation is 8 mu delta. This is due to the positive yield lines. This is due to negative yield lines. So total internal work, in that case, the total internal work done will be equal to 8 mu delta plus 8 mu delta, which is equal to 16 mu delta. Okay, so what we have done, we have split this into 2 halves, internal work done. One internal work done by negative yield line and internal work done by positive yield line. And after that, we have simply added both the equations to get the total internal work done in the slab, which comes to 16 mu delta. Now we will see about the external work done. Again, this will have 2 parts, external work done. It is for the positive and negative. But what happens is, when we say external work done, the total load, that is W, acts on the entire segment. or x on the entire slab together. So when it comes to external, it doesn't get divided into negative and positive separately. It's a whole one quantity of load that is acting on the slab. So it will be only WU. Okay. So load, but we have 4 segments with us. Okay. So if this is the diagram, it is divided into 4 segments, that is 1, 2, 3 and 4. Of course, it has negative yield lines. I have not done the detailing just to show you the segments. So there are 4 segments here. So to start with, if you want to write the equation, it is summation WU into AS, that is area, into delta G, that is center of gravity. Okay. So again, this is at delta by 3, AS is area of the triangle and WU will remain the same. So WU, area of triangle, is half into base into height, and this is nothing but delta by 3. So WU, half, base is L, this is L by 2 into delta by 3. So this is WU into L square by 12 into delta. Now this is for one segment. Therefore, considering 4 segments, external work done will be equal to 4 multiplied by WL square by 12 into delta, which is equal to this. Just cancels out and you get WL square by 3 into delta. So, the external work done, final equation for external work done is equal to WL square by 3 into delta. So we have derived the equation for internal work done and external work done. So it is very simple. You have to just equate internal work done equal to external work done. So when you are writing internal work done, it has to be the total internal work done, which is we have calculated as 16 mu into delta, equal to external work done is nothing but WL square by 3 into delta. So here delta and delta gets cancelled and we get the equation for movement, which is equal to WL square by 48. Okay, so this is the amount of movement at which a fixed square slab will collapse or fixed square slab will fail. So this is again the derivation for movement or yield movement when the slab is square and has fixed edges. So there are 2 yield lines developed, positive and negative yield lines. So it is basically, again we have followed the same procedure of writing equation for internal work done and external work done and simply equating it. Okay, so every time when you will be solving yield line or you will be doing yield line analysis by virtual work method, it will be the same procedure. First you have to write equation for internal work done considering all the yield lines, and you will have to write the equation for external work done considering uniformly distributed load. So here we have done, now with both the videos we have covered case 1 and case 2, that is a square slab, which is simple and they are isotropically reinforced. That means MUX, that is movement in x direction, is equal to movement in y direction. In the next video class we will be doing a rectangular slab which will be simply supported, and fourth case will be rectangular slab with fixed edges. Okay, thank you.